Welcome to The Explainer. Today, we are cracking open a really clever formula. Think of it as a universal translator for logarithms. It's the key to solving any log problem with pretty much any calculator you have. Let's get right into it.
Oh, you have absolutely been here before. I know it. You're staring at a problem, something like log base 3 of 20. And then you look down at your calculator, and all you've got are two buttons, a log button, which is base 10, and an ln button, which is base e. It feels like you're trying to hammer in a screw, right? You just don't have the right tool. So what are you supposed to do?
Well, that's it exactly. It's basically a language barrier. Your calculator is totally fluent in base 10 and base E. But the problem in front of you, it's speaking in base 3. And without some kind of translator, they just can't talk to each other.
And let's be real, this is how most scientific calculators are set up. You're kind of stuck with these two default languages. But what if I told you there's a super simple way to translate any base into a language your calculator can actually understand? And this is where our hero of the day comes in, the change of base formula. It is such an elegant, clean solution. It's the perfect translator we need to bridge that communication gap between the math problem and your calculator. So here it is. The real power of this formula is just how flexible it is. It says you can take the logarithm of some number x in any base b and convert it to a brand new base k. And here's the best part. K can be anything you want it to be. You just make a fraction, the log of the original number goes on top, and the log of the original base goes on the bottom, and you write them both in your new chosen base. Now, while you could technically use any base 7, base 52, whatever, to make our lives easier, we almost always pick one of the two buttons we actually have on the calculator. And most of the time, we just default to the natural log, ln. So the formula you're going to use day to day is just this: the natural log of the number divided by the natural log of the original base. It's simple, it's clean, and it works every time. All right, so theory is one thing, but let's actually put this translator to work and see the magic happen. We're going to run through a couple of examples so you can really see just how powerful and easy this is. Okay, let's go back and crush that original problem. To figure out log base 3 of 20, we just rewrite it as the natural log of 20 divided by the natural log of 3. So you grab your calculator, you punch in ln of 20, and you get about 2.99. Then you punch in ln of 3, and you get about 1.09. You divide those two numbers, and boom, there's your answer, about 2.727. You just solved a base 3 problem using a base E button. How cool is that? Let's do another one, just to prove it's not a fluke. We all know that 4 to the power of 3 is 64, so log base 4 of 64 has to be 3. Let's see if the formula agrees. And just for fun, to show how flexible this is, let's convert to base 2 this time instead of base E. So we write it as log base 2 of 64 on top over log base 2 of 4 on the bottom. Well, we know 2 to the 6th power is 64, so the top is 6. And 2 squared is 4, so the bottom is 2. And what's 6 divided by 2? It's 3. It works perfectly, no matter what base you decide to change to.
Okay, but this isn't just for punching numbers into a calculator. For those of you in Precalculus, this formula shows you something really amazing about functions. If you take a function like y equals log base 4 of x, you can use the formula to rewrite it as y equals ln of x divided by ln of 4. Now, check this out. ln of 4 is just a number, a constant, so you can think of this as a constant 1 over ln of 4 multiplied by ln of x. And what that means is that the graph of log base 4 of x is really just the normal natural log graph, but it's been vertically squished by a factor of about 0.72. It shows that all these different log graphs are just transformations of each other.
Now, this formula is awesome, but I gotta be honest, there is one classic, super common mistake that students make all the time. So let's just tackle it head on right now so you never have to fall into this trap. The confusion is always the same. When you set up that fraction, does the log of the original base go on the top or does it go on the bottom? And believe me, if you mix this up, you're going to get the wrong answer every single time. So here's a little trick, the mnemonic device, to get this right 100% of the time. Just remember this. The base of the log goes in the basement of the fraction. The basement is the bottom, the denominator. So for log base 3 of 20, the log of 3 goes in the basement. It sounds a little silly, I know, but trust me, you will never, ever forget it. So why are we spending all this time on just one little formula? Because it is so much more than just a cool trick for your calculator. This is a really fundamental concept that opens up doors in all kinds of advanced subjects.
Seriously, think about it. If you're going into computer science, you're going to be living in a base 2 world when you analyze algorithms. If you study physics, things like sound and earthquakes are measured in base 10. And if you take calculus, the entire world of logarithmic derivatives is built on the natural log, on base E. This formula is the bridge that connects all these different mathematical languages.
But let me give you one more really cool real-world example. When astronomers are trying to measure how bright stars are, they use a system called magnitude. And you guessed it, it's a logarithmic scale. It's the only way they can compare a really dim star to a super bright one and have the numbers make any sense.
So what base do you think they use? Is it 10? Is it E? Is it 2? Nope. They use this really weird specific base, approximately 2.512. I promise you, your calculator does not have a log base 2.512 button. So astronomers and their computer programs are using the change of base formula all the time, constantly, just to make their measurements usable. It just proves how essential this translator is out in the real world.
So there you have it, the change of base formula. It's just a simple little ratio, but it unlocks this whole universe of possibilities. And it kind of leaves you with a bigger question, right? What other rules that you've learned in math are really just universal translators in disguise, designed to help different parts of mathematics all speak the same language? Thanks for watching.